Okay, this time we are going to take an overview of the MIPS machine, right? So you have to take note of few things, right? We are going to do some kind of assembly. It looks like assembly language here. So that's what we are going to do. Now, you realize that for MIPS assembly is more primitive than higher level languages. When we talk of it being primitive means you need to be more explicit, like you have to kind of imagine the hardware will do it when you are trying to do it. It's also very restrictive and yeah, a whole lot. However, no matter what we are going to do, its whole point is to introduce us to design goals, right? The main design goals is to maximize performance, minimize cost, and also reduce design time. Normally, these factors trade off no matter which architecture you are going to use. So there are few things you have to take note of, and one of them is the ISA, right? The ISA is more or less how the programmer views the machine. In what sense? When the programmer is programming the machine, what kind of instruction can he give the machine? What kind of registers does he have access to? Those are basically the ISA. In as much as we are doing it, we'll be taking note of things like the memory model of the MIPS machine, and the instructions, yes, and we have instruction. We could be taking things like the formats, the types of instruction, and the modes, right? Yeah, and also take note of various operands we'll be using. And yeah, so start with MIPS arithmetic. Well, all MIPS arithmetic instructions have three operands, right? So three operands means it's kind of thing they have three elements, right? It is wrong if you say they have three registers, but yes, all arithmetic. Take note, all arithmetic. They didn't say load instructions or branch instructions. They said only arithmetic, right? So arithmetic is something which has to do with addition, subtraction, multiplication. So for example, is this instruction. Now you realize that the instruction has is called add, right? And it has S0, S1, S2. Now don't be scared about what you see. Actually, in MIPS assembly, most of what you'll be doing are with registers, right? And this S0, S1, S2 are um, registers which are used in the MIPS architecture, right? So unlike C or any other language where you can declare the variable and give it the name you want, MIPS has already kind of giving you the variable it has available to use, right? So apart from them, you can't use any one of them. And again, and most these variables are this S0, S1, S2. You can conceptualize this as that, right? So this instruction is simple. It's just saying that what is stored in S1, add it to what is stored in S2, and store the results in S0, right? That's basically that. Now, as we go about, you may realize that the whole point of this course is actually to introduce you to design principles, right? And one major design principle is simplicity favors regularity, in the sense that if you have a very simple format, right, then you are more likely for a simple hardware, right, and you get regular instructions, right. So you realize that when we are transitioning from add to subtract in MIPS, realize that we don't change much. So this is add instruction, this is subtract instruction. But see, they look alike in terms of the number of registers we are using, right? The number of operands we are using. And that's the basic principle of simplicity favors regularity. But with that, you realize that there are some instructions which if you go strictly by this, right, you'll be forced to give more codes per instruction, and we'll see that in the later chapter, right? But for now, let's take it step by step. So it says operands might be in registers, only 32 registers provided, which require 5 bits to select the register. Simple. What it's trying to say is that in MIPS architecture, each register is 32 bits wide, right? And because each register is 32 bits, right? No, in terms of addressing, We need a total of 5 bits to select any of the registers, right? So that will come in the part where we are storing instructions. So don't worry much about this part, but it's saying that in terms of storing this instruction, in terms when you're writing a machine code for this one, this will be a total of 5 bits. This will be a total of another 5 bits. This will be a total of another 5 bits, right? So it's basically something like that. Would go into details about that, right? Now, another design principle is smaller is faster, right? And that's if you have a very small case scenario, if you have a scenario where you can make you can you can optimize very small part of an instruction, it is more preferred than having one big instruction. This is what I mean. For instance, some architectures like um, the complex instruction set architecture have something like um, a string copy command, right? Or an add command which can add three numbers, right, at a go, right? Now, MIPS says no. Why don't you add the numbers two at a time, right? Yes, and because realizes that this is a very smaller way of doing it, and it's better. Now, the next part is where we deal with registers and memory. Arithmetic operations must be in registers, and MIPS has 32 registers already stated. Now, what about programs with lots of variables? Now, if you have too many variables in your program, in fact, if your program is using more than, let me see, maybe more than, let me say 32 registers at the same time, right? Then probably you may need to store your other variables in memory and retrieve them as and when you want. You might see an example later on, but that's it for now. Now, organization and memory organization in MIPS is quite simple, right? Now you can view it as a very large single dimensional array, which is accessed by address, right? And this is no different from your concept of array in C, right? So except that this array, um, this is just a whole block of memory stack, right? And that's how in the context of memory, that's how memory is viewed in MIPS. However, would see in a different scenario that actually in MIPS it is word addressable by a different methodology. So actually it's here. It says bytes are load and store units, but data items use larger word, right? Now in terms of storage, right? MIPS conceptualize it in terms of you are storing bytes, right? But when you are considering say a whole data item, right? MIPS conceptualize it as a word, right? So usually most of what you see is you have 32 bits of data. So this is kind of the memory stack in MIPS, right? How the memory looks like in MIPS. Now you have 32 bits of data, 32 bits of data, 32 bits of data. I realized that each one is a word, right? So each one is a word, each one is a word, each one is a word. And now this 32 bits is made up of what? 4 bytes. So you can divide it into 4 sections, right? You can divide it into 4 sections, right? Yes, so 1, 2, 3, and 4. That's the each 4 sections, so 4 bytes, right? But each one is a word, so each line is a word, each line is a word, each line is a word. That's what MIPS is saying. And there's the concept. It MIPS the total number of bytes, right? The total number of these small boxes is 2 raised to the power 32. However, because each of 4 of these small boxes make up one big box, right? 4 of them make up one big box. Then it means that we have 2 raised to the power 30 big boxes, right? So that's what it's been explained here. There are 2 raised to the power 32 bytes, right? With byte addresses, right? In MIPS. So you can give a total of 200 2 is the power 32 addresses, different addresses in MIPS. However, you can only state up to 230 different words, right, of addresses in MIPS. Now, you realize that they also say that the words are aligned, right? And that just means that it is illegal to have certain type of words in MIPS. So you can't access, say, word 2 in MIPS because word 2 is not um it's not divisible by 4, but you can access word 4, word 8, word 16, right? But you can access byte 2, byte 1, byte 0, byte 4. As for the byte, you can access any number. But as for the word, because MIPS is word aligned, you cannot access word 2, like something which is not a multiple of 4. It's more of a technical detail, so we may view more of it later. But one last thing before we bring the video to an end is there are also other type of instructions. So we've already looked at the add arithmetic instructions and the other type of instruction, and these are load and store instructions. And an example is what you see. It seems like we have an array A, right, and we are trying to take the eighth element of the array. We are trying to add H to that eighth element, right? Now, how will MIPS assembly see this? So this is like your pure C code, right? So this is like your pure C code. Now you realize that the value H, right? MIPS will first, when we are trying to write it in MIPS, we intentionally first store it in a register, and you realize that the location of the offset, right, from the base address A, right, is multiplied by 4 to get the actual address where we'll be writing to, right? Now the base address A is stored in what? F3, right? Now I think I should show it practically. So let me show you a MIPS machine and explain what I'm doing actually. Yeah, I think an example will make it clearer. So let's see an example. So here we are in a simple MIPS machine, right? It's just a MIPS simulator. And it's actually the same question you saw there, which I'm trying to emulate here, right? So this that you saw is what I'm trying to emulate inside the MIPS simulator. And you realize that I have a bit of instruction. Now, don't worry if you don't entirely understand this whole thing, but it will work as you go step by step. So the whole point is this. The question was trying to add 8 to um trying to add h to the eighth element of an array, right? So now let's assume that the h is 4, right? So it means that this I'll store the 4 in a register. That's the first part. So I'm storing that 4 in the register h2. So in your head, just assume that um, s2 is equal to h, right? Then the next part is I have to find the address of the base address of the array. Someone asks, how did I get the base address? Well, it's simple. I MIPS has a data a data how do you call it, a data block, right? And one of those block is 0x1001. Now we'll see that later, so don't worry. So that's the base address, right, of the array. Now on the eighth element of the array, which is what, 32, right, I'm trying to load the content from there, and to that content I'll be adding my h. So that content I'm adding my h. Then after I'll save the content back. The SW means store word. So let's go and see it procedurally, right? So let me try to assemble this. Okay, so this is the way to be assembled. Now if you were wondering where I was getting my 0x 001, right? And that address is here, right? As you can see, it's in the data segment. Now you realize that um let's assume that all these were storing numbers, actual numbers in array. I can't go and add numbers manually, but let me add numbers to some few places. So let me add here like 3. And now let me go to the next block and add what, 6, right? Yes, so something like that. But you can store numbers throughout here, right? Now, when you're executing it step by step, the first step is you have to get your age, right? And that's the first step. So when I execute the first step, you realize that from here, you realize that S2, right, will now be storing the value 4, right? Because I'm saying age is 4. So you see it. And the next part is I have to store my address into a register, and I'm storing it in register S3. So you realize that register S3 will now come to store this address. And you realize it's 0x1001000, right? Now, the next part is that I want to go and get from memory what is stored in that 0x100 whatever whatever. And you realize that it is not exactly here that I'm coming. I'm going 32 bits from that position. Right now, this is 8, this is 0, 4, 8, 12, 16, 20, 24, 28. Right, so this is 28 bits from that position, and this is for the 32 bytes and 32 bytes from that position. So it's supposed to be loading from here, right? Now let's see. So you realize that P0 is now storing with 0x0006, this 6 here, right? Because it is 32 bytes from the base address, as you can see. Now, the next part I'm trying to do is that I'm trying to add to the data I went to fetch. I'm trying to add the H to that data, right? And that's what you can see. So I'll store it back in T0. So I'll say T0. I fetch the data in T0, right? So I'll say add into T0, the value stored into T0, and the value in what? S2. Remember, S2 is H. Now, immediately I do that, realize that T0 changes from 6 to A. Remember, we are in hexadecimal, right? And it was storing what? 6 at first. But I've come to add 4. 4 is, so 6 plus 4 is 10. And 10 is A in hexadecimal. Then when I'm finished, the last part is say I should store the word, right? So save word T0 into the same location. So realize that this location and this location are the same, right? So realize that at the end the A will come and be stored here. So you realize that it has changed to A. And that's the concept the same question was trying to give. So yes, you have to remember that the MIPS arithmetic operands are registers and not memory, right? So that's why we're suffering moving from memory, bringing it back and everything, right? But after that, we've been successfully able to do that.